We're going to talk about managing soil moisture for produce yield and quality. And I think a lot of the things we've learned this entire day fit into this very, very well. I just dropped this slide in thinking about what Grant was presenting this afternoon. This is down in the Green River area, but we have some very salty soils. And this particular field, it's been under irrigation probably about 10 years, but there's a lot of dissolved gypsum in calcium sulfate that's come to the surface there. And then not only comes to the surface, but it drains off in subwater and even runoff. And that little chart up here, that's the Green River. And this is some of the water coming off those fields from some samples that were sent into the USU lab. And I have similar samples there. So we do have some salinity problems. And if they get bad enough, it doesn't matter how much water you put on there. You're not going to grow any crops with them. So there's a lot of things that impact our produce yield and quality. Genetics is a big one. Our climate is important, disease, pests, fertility. And I'm going to talk about soil moisture. And soil moisture alone will not give you the best quality if we're lacking in other areas. So just to give that upfront disclaimer. I did some research the last couple of years, particularly on onions, where we're comparing drip irrigated onions to furrow irrigated onions. And our main objective was to see how much water we could save, and not just water applied to the field, but water that was actually lost through evapotranspiration, or what we'd call depletion. Because runoff returns to the system, and so does deep percolation, at least in this Bear River Valley area, and this is in Weber County. So we put in soil moisture sensors after the onions were up, but before the first irrigation. And we put them in very carefully so that we didn't kill any onions, so that we'd have a good representative area. And this is just one place where we run our sensors in the ground and we set them up. There's through the field. I tried to get the top of the field, the middle of the field, and the bottom of the field on furrows, and then kind of a diagonal on drip irrigation. And we put in a lot of sensors, 10 sensors. And these sensors were very high quality research sensors that measured a lot of things, but I'll just talk about the moisture that they measured in percent. Oops. So I'll take just a little time on this slide. So this is the different depths of the sensors. So remember, we had 2 sensors in the bed, which is, I think the bed's about 17 inches wide, and then the furrows was about 11 inches in that, or 17 or 18 and 11 inches. But you can see this gray one and this orange one here, that's the shallow ones. So this is in the middle of the summer in 2019. And you can see during the day, some water moves out of that upper layer, and then at night it levels off. And sometimes it even goes up a little bit as the water moves from a wet area to a drier area. So the top 2 did like that. And then these are the next 2 down in the bed. They're the 10-inch depths, which is these. And these 2 right here, you can see they do the same thing. So they dry up, but they don't dry up quite as much. And so I could just tell you that the top plant roots are concentrated in the shallower depths. And if water is available, that's where they use it first. And then these are in the furrows here, and then the deeper depths. And this is the number 10. That was the one at the very bottom. And this field was surface irrigated, so they put on about 60 inches during the year, and the plants probably used around 25. So a lot of extra water and a high water table. But after the irrigation, you know, the irrigation might have been 5 or 6 inches. And so it fills up all these layers of soil. And then after about a day, when they turn the water off, it starts to drain out. And so it drains out in a day or two. And if we take all those individual readings and multiply them by the area they represent, we get a depth of water. And that's what these represent. So here on this surface irrigated field, you can see that they all move together and their slopes are about the same. So that's how many inches over a period of time that they remove. So, you know, maybe around 16 inches, and these irrigations are every week, and then it usually drops down to maybe 13 or so inches between the next irrigation, but about 1 inch of that is probably just deep percolation. And then we have surface evaporation that we're actually not measuring here because our first sensor is about, it's between kind of 3 and 7 or 8 inches deep, so it doesn't get the very surface. But from that, we can get an ET rate. And this is kind of the ET rate from the soil moisture, not from the surface. So you can see our deep drainage and then these slopes of these line, which is about 0.2 inches per day. But we would be more like 0.25 if we added the soil evaporation in there. And Mike covered this, and everybody has a different chart, but our soils are about in the order of 40% voids. Some sands could be much less depending on how they're structured. And then the available water, it is greater for these heavier soils, but it's all available, but some of it's readily available, and some of it, the crop will begin to be stressed to get all that water. The crop won't die, but it will not yield as high and will not be as good a quality. So really, even though we show maybe 20% range there, which 20 times 12 is 2.4 inches, it's not all really readily available. It's all available, but not readily available. And we might look at that. If this was just the voids in our soil, so the parts that is not mineral or organic matter, then we would have this amount of water that's in the big pore spaces that drains away rapidly. If you think back to that graph we saw, the water that drains away in a day or two. And then this water is held pretty tightly by the soil, except for it's available to plants. It would be very slow drainage, and it would be in the smaller pores. And we really want to only use this amount of water that goes from this middle line up to the top line. And so that's only about half of that, and it depends on the crop. Maybe alfalfa and wheat, we could go down lower, and maybe we'd want to only use 40% for beans and onions and some produce at certain stages. And then this water is not available. To get that water, you'd have to dry it in an oven and heat it up and let the sun shine on it, and it would pull the water away. And so our water availability does control our ET, in addition to the climate data that we saw. So here's just kind of the same drawing, but just to sum that up, a typical soil would have about 5 inches of voids. And so at saturation, in a foot of soil, we'd have about 5 inches. And filled capacity is about 3.5 to 4 inches in most of our soils that we farm. And our allowable depletion would be 2.5 to 3 inches per foot, but our managed allowable depletion would probably be on the order of 1 to 1.5 inch. So that's what we'd want to look at, is this 1 to 1.5 inches. And to be safe, depending on your irrigation system and your soils, maybe 1 inch per foot would be on the conservative side. And then the wielding point, we still have 2 inches of water in most soils, but it's not going to be available as readily, and not at all at some point. And so here's just saying the same thing. If we're looking at very shallow rooted vegetables that are on the order of a foot or 18 inches, we probably have 1 to 1.5 inches available. But that could be increased when we spread out wider. It depends on how we calculate it. Corn, tomatoes, and squash, by the time they're more established, they've got a bigger root zone. So, you know, it might be twice that much because they might be down 2 to 3 feet. And asparagus might even be down 4 or 5 feet. So they have much more available water. I'm going to talk about a few methods to estimate our soil water. And one good method is to feel. So we'd scrape away the top of the soil and it's grab a handful of soil. And if we squeeze that soil and our hands come away wet and we make a nice ball here, we're in a pretty good soil moisture availability percentage. So we're 75 to 100. And if we can squeeze it and make a ball, not much is sticking on our hands, and this is for our sandier soils, then we're probably still okay. But if we get a crumbly ball, then we're too dry. Even though there's still soil moisture in there, we're getting down into the 25 to 50. And I think for a lot of the things we want to grow, at least during the critical period, we want to stay in this range. And if we look at a sandy loam, it's similar, but just because we have less adhesion from the clay, it crumbles a little different and looks a little different, but it's still kind of the same thing. Here your hand gets wet. Here it might get a little wet, but not much wet. Here you might even get some mud on your hands. And here it's probably more like clay, and this is getting closer to mud. So just a good way to give a good quick check on your soil. Another common way to do it, and these are probably some of the least expensive soil moisture measuring devices that are available. And they don't actually measure soil moisture, but they measure a thing called soil matrix potential. They don't even measure that. They measure salinity and then change it to a soil matrix potential. So the more water that's in the soil, the higher the conductance, and it sinks into so they're measuring resistance in that soil. But 0 is if the soil is saturated, it's at 0. So 0 is like the top of a lake or the top of the ditch. That's 0 pressure. So that's just atmospheric pressure. And then if we go negative, see these numbers are negative, but we've got they look positive, but it's getting drier as it moves up. These numbers get bigger, it's drier. And that's just the way they read them out. And so this 100 is 1 atmosphere. Field capacity is probably just a little below that 50 line. And so that's about where our water will drain to with gravity. And I would say for most vegetables and produce, we'd want to stay 100 or below, or maybe even 80 or below. And we wouldn't want to get up here in this dry area. And this was just one where you can see we went a long time, like a month and a half without an irrigation in a pasture. And so that's why it got so high in numbers. But down deep in this place, we had a water table, so it stayed much wetter, just the capillary action. And here's one without a water table. And this is pasture, but it's the same for all plants. We had a lot of water up here. We were irrigating, and then we stopped irrigating just to see what it would do. And you can see the top layer is what I said changes the most, and the deep layer changes the slowest. But we went from, over 13 inches down to about 6.5. So we roughly dropped 6 or 7 inches of water out of that soil. But see how flat that is down there? There was not much ET going on as compared to here where we've got the steeper slopes. And this is a fairly long period of time, so those slopes are steep. But so not much production through this period, but the plants are still alive, particularly because these are pastures. Now this is what I wanted to share with you. I think that probably gives some good information is this wasn't part of this study per se, but when I got looking at the data, our highest yields were in 2 surface irrigated fields that actually used drip to establish the onions. And then I got looking at the yields. If I take from the head of the field to the tail of the field, the yields dropped off a little bit at the very end. And then when we look at the soil moisture drops off a little bit at the very end. In this field, the soil moisture was okay, but they didn't use a drip system to establish it. And so they didn't get a good stand, and they had a hard time establishing the onions. So their yield was, less than half of what this surface irrigated field was. We actually missed one reading here, and it would probably be down here because this field in 2020, they applied 25 inches of water. So not too much for the whole crop of onions from beginning to end. And this field, they applied 20. But this one had the irrigation design was not as good as for this one. So this one had more irrigation uniformity problems. And then this field here also had irrigation uniformity problems. But see, just in this case, we went from 100,000 pounds per acre down to about 65,000 pounds per acre. But in a drip irrigated field, these fields are all planted within a day or two of each other, all the same variety of onions, and were all harvested within about a week of each other. And so you can see this field was much more uniform, although the yield was less the further we moved away. And Mike may have showed this. Well, I don't think he did, but so this is that one field. Here's the inlet, and we had a sensor here, a sensor here, and a sensor here. So these 2 sensors are approximately the same distance away. This one's a little closer than this one, but this one here is way out there. And then when you look at, from a satellite, looked at and calculating the NDVI, the normalized difference vegetative index. So the greener the field is, the more biomass, the darker the green is. And this area here has less green, less mass, and less yield. And so you can see that uniformity of that irrigation system, even though it's drip, is not that great. And that's because of the small pressure difference, and they didn't have pressure compensating tape. And just before I leave this OneSoil application, it's really good. It may not work on very small fields, but it has about a 10 meter pixel by 30 by 30. And so you could get 30 by 30 there anyway would be the size of the pixel, but it'll calculate this, and it's a free app. So this is that drip irrigation field. So the 2 that were close, about the same amount of water. The one that's far away, it just got drier and drier. The ET was less, and the yield was less. But in the surface field, we had fairly uniform irrigation because they just soaked it every time. This is the bottom of the field where they don't plant the crop, and so the turning area and the drainage and the ponding area. So you can see that that's pretty uniform, that field, surface to drip. So I think the farmers are just kind of learning about those. And here's the different soil moisture follow each other really well. Here's another drip field. It shows the difference between the flow meter and the end of the field. So drier, drier, drier. This was, I think, 65,000 pounds per acre, 80,000 pounds per acre, and 100 and something thousand pounds per acre. So soil moisture makes a big difference in yield. And when you're applying irrigation with soil moisture, it's with your water, if this is getting 20% more water than this, then it's getting 20% more nitrogen too. So that makes a difference in your yield also. And here's a surface irrigated field. You can see it's much more uniform because they just don't, they over irrigate, and the onions don't seem to care if they're wet. And this is only irrigating every week, but it really holds enough water that, and the onions do well even though they're over irrigating, but they don't have a choice. It's just how a surface irrigation field runs sometimes. And here's kind of the average of all the sensors in all those fields. So you can see our poorer yielding field is down here. our higher yielding fields are up there. I think this slide was shown by Mike, and so this has a exponent of 0.5, which means it's not pressure compensating. It's just the same as a sprinkler. It's just an orifice equation. And so if you had a big field or different elevations, you can buy drip tape that's pressure compensating. It's more money, but if you're in a small scale, maybe you can buy more expensive tape and use it multiple years, where this is just used 1 year and then they pull it out and don't use it the next year. And just the same uniformity. And I think this is one thing that we have to remember on all irrigation systems. They don't apply water uniformly. And so if we just apply exactly what the plants need, half of the area is going to get too much water. Like, so here's a line that's 80% coefficient of uniformity, here's 90. And half the area is going to get too little water. And too little water will impact yield and quality. And too much water, at least in the case of onions, where fertility was not an issue, didn't seem to impact yield. So if you apply less, it even gets worse. Maybe only 25% gets fully irrigated and 75% not. And this is probably more where you want to be, is where almost all the field, for example, if we needed 25 inches for the season, almost all the field would get 25, and maybe you'd have 10 to 25% that'd be under irrigated. And you have this that'd be over irrigated. But what it costs to put that water on, if it's available, is very little in comparison to the yield differences, which could be 20 or even 30,000 pounds per acre. So you can imagine the cost of under irrigation is pretty expensive. So here's where we did the yield sampling in those fields. And so these are the comparisons, surface kind of in paired fields near the same location. And you can see that in one case, the drip did better than the surface, but that's where we had a poor stand. And then the other cases, the surface did better, simply because they were kept wetter. And we didn't tell the farmers how wet to keep the field. We just let them irrigate as they chose to and as they were able to. But this is just one example of both drip. If you had a good market for 3-inch bulbs, then, you know, this field did well. It got about 50,000 pounds of 3-inch bulbs, and it had a high stand, and the average was 84,000 pounds. But here's a drip field that had 110,000, and it had a little lower stand, but most of its onions were 3.5 to 4 or 4+. So I'm doing this with onions, but it'd be applicable for beans or corn or pumpkins or watermelons, whatever you're growing. It's kind of the same thing. So and then this is the percent of the crop, and then this is the yield in. This is bulb count, and this is pounds. And this just shows that we actually need a pretty good stand to get a pretty good yield. If we don't have a good stand, even if these down here were kept very wet, but there just wasn't enough onions to get a good yield. So I think I'm about done with this time. So these are just some observations I made, and you know, I've just been following this closely for a couple of years. I've been working, you know, 40 some years with irrigated agriculture, mostly on a large scale, but you need a good establishment, high populations for a good yield. And the surface irrigators, they've been doing it for 100 years. I think they know how to apply enough water. And there was the drip irrigation, I think, you know, fairly new, relatively new, maybe 4 or 5 years, but you think you have a great system, and so maybe you just really cut back on your water, and then you hurt yourself, and then you don't get the yield. And so I would just recommend that you monitor your crop in the low water delivery location, and you walk around your field often and see what's happening, and then just get a good design irrigation system. And if you've got elevation differences, then you need to go with a drip system, or just put a lot of thought into the design and use some pressure regulators and other things so that all your drip tape sees about the same pressure. And then just remember that if you're fertigating, you want a good uniform system because you want your fertilizer to be applied uniformly. So at least last year, 25 inches seemed like a good number for a drip system, and produce good yields. And so these are some of the yield differences that you can have. And the fuel to run those systems is not very much, just a couple gallons an hour compared to these big yield differences on 20 or 30 acres or 100 acres or even 1 acre. So just a couple things to think about. And then we'll get into it in the next presentation, but there's a lot of factors that influence water use, and there's times that are more important than others. So we'll talk about these other things on our next one, but we need soil moisture and fertility, and sometimes they go in the opposite direction. Sometimes too much fertility is too much vegetation and not enough flowering, and sometimes too much water at certain times is too much vegetation and not enough flowering. And so it's something that takes a little of experience, and I've worked with a lot of farmers, and we grow green beans. We used to grow green beans on our farm, and we grew a lot of crops, and you kind of learn how to do it with a little experience, and it's hard to explain it to somebody. So I think that's all I have on this one, and I haven't looked at the questions, but I think I could probably pull those up. Maybe if we've got a minute or two,